There are also automorphism for questions actually. So
Uh,
we have to show that automorphism of H cross automorphism of K is a subgroup of automorphism of H cross
Automorphism of H cross automorphism of K.
automorphism of K is a subgroup of automorphism of in मतलब content in automorphism of H cross.
Okay. I mean, okay, let's see. This is a little bit. Hmm. So this is all that is said, nothing more about H and K.
H and K must be a subgroup of same group, I guess. Nothing is given more.
Okay, but I don't think that is important because H cross K will not be a subgroup of anything, right? Of G, right? So maybe that's not very important, that condition. Like if this and this are contained in G, it doesn't say anything about H cross K, right? So, well, okay, I think one Vaishnavi is disappeared. Okay, I mean, look, yeah, so first question is what is H cross K, right? So H cross K here we are interpreting as Cartesian product of groups. I mean, or maybe a Cartesian product is direct product, right? We are interpreting this as direct product of groups, right? Which means that the multiplication is pointwise, okay? So for example, if you take this and this, then the output is this, where H1, H2 ka multiplication is determined by that, and this is determined by multiplication in K. So this is the operation we are assuming, because when you say H cross K, usually it is interpreted like this. Right. So automorphism of a group is obviously again a group. But why is automorphism of H cross automorphism of K sitting inside this? So see, it is certainly not a subgroup, right? It is not a subgroup in that sense, because as a subset, this side is not a subset, you see. So we will not write this to begin with, okay? What we want to say somehow is, some connection from here to here. So basically, let's see, I mean, if F is given, if F is given and G is given, and these are automorphisms, then you just want to produce an automorphism of H cross K. So how will we produce? I'm writing it like this, but the definition is important. You just send H comma K to FH comma GK. And then this is an automorphism that we can check. Correct? You see, this thing is just a notation. It's a suggestive notation, but it's just a notation. So what you need to check So you just need to check number one, that this is a group homomorphism, right? It's a group homomorphism. That I am not doing. And also check that this is our is, I mean, just write it properly, is 1 1 and on 2. These are the two things you have to check, and you can easily check it, right? There's nothing to do. So just check, just check now and tell me if this is working. Yeah, is it okay?
Can you just show the 1 1 and on two?
Yes. It is just a set. Set is just, so suppose that you want to check 1 1. Let's see if it is 1 1. No, but it's fine, right? Why is it a problem? So where are you getting stuck if you're trying to show 1 1?
I just need the figures.
You need to write the definition of 1 1, right? Just write the definition. So F cross G, and then you have this is one input is equal to F cross G. This is another input, right? Vaishnavi, please tell, like, can you say what to do for this? How
Yeah.
to,
Okay. It's f of h1
right?
comma f of g of sorry g
Right,
of k1
correct,
equal to
right?
f of yeah 1 to 1. There is no problem.
Sorry,
Okay. Like next we have to write h1x like conjugate f of h1 is
conjugate.
yeah.
How is conjugate
This
coming?
is okay.
This is just an automorphism. Automorphism is just a 1 1 onto function from set from that thing to itself. It doesn't have to be
Okay.
conjugate, right? Conjugate is what is inner automorphisms. We don't, but these are not inner. This is arbitrary automorphisms, right? Just 1 1. Just tell me why it's 1 1. Well, it is 1 1 because this implies that h1 equal to h2, right? First, so this is just a tuple of ordered pairs. So this is equal to
Yeah.
this. So h1 is equal to h2. This is equal to this. So g1 is equal to g2. K1 is equal to k2 because g is 1 1. This is what are we doing even, right? Yeah. So you can, this is nice. And this onto also you please check. Okay. Yeah. Not going to do that. So you can check these two things. It's just a matter of writing. You have to understand that this is now a group element. and this is the multiplication, this, follow the steps and it just comes, right? Because the multiplication is so straightforward, right? It has to come. So it is fine so
Yes.
far, right? Right.
Yes.
But this is not but I mean, this is what we have just said is that you are looking at this thing as a set. If I'm looking at this thing as a set and looking at this thing also as a set, then I have given you a map, right? I've given you a map which is taking f comma g to f cross g, which I have defined. Okay. By the way, to check that f cross g was 1, 1, you can do it obviously in better ways, but I will leave that for you to think. That in groups you can translate things to the origin. Basically, you can use that, but that you can. So automorphism, I think the definition, as I'm saying, is just a group homomorphism, which is bijective, right? And from the set to itself, from group to itself. Okay, so we have given this map, right? But now we should ask questions about this map also. In some sense, that is the thing to do, right? This association, because in fact the question is asking that it is sitting inside, right? The question is asking that it is sitting inside. So what is a good notation? F comma g.
Actually, the question was given that the phi is not isomorphism and the automorphism H cross automorphism K will contain in that group. That was actually given.
Right. That is, then we have to do all that, right? Then we have just done a very small part. So now this phi which we have defined, okay. So first of all, notice that, I mean, you know that this and this both are groups, right? Both are groups under the obvious things. And then you need to check that this phi that I've defined is the phi is a 1, 1 group homomorphism. Now, once again, this is just a matter of writing, but let's write it because, you know, maybe if it's the first time you're doing, but. So first check that phi is a group homomorphism. So how do you do that? You just have to consider phi, and there will be two things, one and another. Now you know what the group is. So we just take two elements from the group and you have to show right? Just have to understand what is what. What, when you get confused, you should ask, what is this? Is it a group? Is it an element? Is it operation? What is the operation? If you can know what is it that is happening, what is this object, then less chance that you are confused, right? Unless you're very tired. So yeah, we need to check this. Okay, what is this operation? So we should ask then, what is the operation on this pointwise? Again, this is a group, this is a group, so you just do product of groups. So product of groups का meaning ये है कि you have to do pointwise because it's a direct product. So do pointwise. right? Now, what is this circle? This is composition, because that is the operation on Aut H. So you have to know how is Aut H a group? Obviously by composition of functions, right? That's the operation, correct? So, so how do you show that this, where is this? This is in the right hand side, right? What is this? Well, let's see. What it is will be known by what it does to the element, right? So you have to take an element h comma k, correct? So take an element h comma k, and then you tell what will be done to h comma k. What will be done? Go to the definition of phi. Phi sends f comma g to f cross g. So this time the f is f1, f2, and g is g1, g2, right? And this function will act on this. And what will it do? That is the definition of that cross, f cross g on h and g1, g2 on k, right? What is this? This is composition, right? So this is like f1 is acting on f2h. F2h is again an element, and g1 is acting on g2k, right? Then you have to be right here. And now how, wait, I have missed some brackets. Right, now what is this? This is f1 g1, this function acting on f2h comma g2h, correct? Right?
The left hand side, right?
Yes, we are still in the left hand side. We are always in the left hand side so far. Yes, I should have emphasized that. This we are not considering, but no need to do all that. Yeah, this is just LHS. Okay. And then what is this? Well, this is f1 g1 that you already wrote. This is f2 g2 applied on h comma k. This is k. Right. Now what is this? What is this? This is phi, right? Phi of f2 g2 applied on h comma k. Yeah, I've written some things wrong, right? So let me erase this. So this is where I went wrong. So let's track back. I think when I so far I think there is no problem, but yeah, but then I mean, look, the simpler way to do, I mean, rather would be just if you don't want to go forward from here, is that you look at this thing and you apply h comma k to this and operate and see that you get the same thing. But don't look at this while doing, otherwise you'll inevitably cheat, right? Without knowing, maybe, right? So just take h comma k and apply it on the right hand side, and you see that you get the same thing. But that's fine. But now this is an element of h, this is an element of k, okay? And this thing is some function applied on H cross K. What is that function? That function is F1 cross G1 applied on this element comma this, means this element, and that element is this, right? That's how F1 cross G1 acts. F1 cross G1 is a function from H cross K to H cross K. And how does it act? Precisely like this, right? Okay. And again, you know that it is this composed with F2 cross G2 acting on H comma K. But what is F2 cross G2? That is phi of F2 comma G2. That was the definition of phi. And similarly, this is phi of F1 comma G1 acting on H. I mean, that is how you know two functions are equal. If you don't evaluate them at a point, how do you know they are equal? In this kind of thing. So it's a group homomorphism. I've not done anything, right? I just written what is what. This is just bookkeeping, right? Not bookkeeping is not a trivial matter. I'm not saying like that, but this is bookkeeping. I'm trying to just say that. Okay, yeah. One you should check for yourself. So this is fine. It's a group homomorphism. Yeah. So it's a 1-1 group homomorphism. Why it is not onto, that you should think for yourself. Why this is not onto? Basically, it's saying that automorphisms of H cross K, there are many more automorphisms of H cross K. You just think, you can think, right? You can take Z, 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 Z cross Z and try to figure out the automorphisms. But even there are some simpler ways to see why automorphism, because they can be mixing. Right? The automorphism that we are considering, in them H and K are sort of separately acting. But obviously in general they can act. I mean, just like vector spaces, right? Take H to be reals and K to be reals, then this is just a direct sum, or just what you know as R2, right? And then you want a automorphism, or whatever. And these are abelian groups, right? R is an abelian group under addition. So obviously you can send 1, 0 to 0, 1 and 0, 1 to 1, 0. But our example doesn't allow the things F cross G don't allow that, right? They act separately on each coordinate, right? You can see that F is only acting on H. But yeah, you should take examples and then see. And I mean, will it never be surjective? That will this phi never be onto? That's not true. It can be onto for some groups. I mean, the trivial groups it's onto, but it can be onto. But let's not get into all that now. Yeah, like basically if it's like there is no morphism from H to K, there is no way to go from H to K. Or let's think. Yeah. So let me erase this and let's think. Can phi be ever onto? Can phi ever be onto? Yeah, that's one of the things to think. Obviously, there are examples when it is not onto. That's okay. But can phi be onto? Let's think about this. Obviously, if H and K are trivial, then it is onto. If H and K are both identity groups, it's onto, no doubt. But in any other case, can it be onto? That's the actual question. So we are looking for some groups, right, for which that phi is onto, which just means that we want to say that, like, if you have any morphism, any automorphism, then it should take yeah, h comma 1. I'm writing the identity as 1. This should go to some h prime comma 1. Every automorphism psi should be of this kind, right? Then only our psi will be in our image. Then psi will be of this type, right? Do you agree? If psi is of this type, if psi is of this type, which takes h comma 1 to h prime comma 1 and similarly, then psi will be like that. You can think like, then it will be, then it's like acting coordinate wise. So let's see. H goes to h comma h. This, I mean, see, maybe this is a little complicated for you, but just let me know. Yeah. But the question is done, because the question just asks is not onto. Not onto means you have to just give some example when it is not onto. Something is not true, something is true means it should be true always, because nothing is said about h and k. Okay, but it is not always true, because you can just take z cross z and so on, and you can find it's not onto. But here we are delving into a slightly different question. So projection to the first coordinate is a group homomorphism, and right, I'll project onto the second coordinate. Right. So can you give an example of a group? Can you give an example of two groups where there is no map from one to the other? For example, if you look at Z mod 2Z and you look at Z, show that there is no group homomorphism. I mean, of course there is, but the trivial one. Show that there is no non-trivial group homomorphism. Okay, yes, you can of course show. Right. Right. So try to show this, that there is from Z mod 2Z as a group under addition. That's the only thing under which it's a group. Okay, multiplication also in this case, but at least Z is not a group under multiplication. Anyways, I'm just, so show that there is no group homomorphism like this. So now you think, now if you put Z mod 2Z, okay, cross Z, and Z mod 2Z cross Z, right? Then you know that this part, this subpart, I am writing, okay, I have to write 0 because cannot, it's hard to write 1 as 0. This has to go to this, correct or not? Because it cannot slip into Z. Z mod 2Z cannot slip into Z, because otherwise you'll get a homomorphism from Z mod 2Z to Z, right? If you compose this homomorphism with the projection onto second coordinate. Or you can just think, just loosely speaking, you understand, right? If there is a map from here to here, if something from here goes into Z also, if there's some Z, it will not work. Then you'll get a map from Z mod 2Z to Z, right? If you forget this coordinate. So simply you can believe this, and then obviously you have to sit and work it out later if you want to. So this part has to go to this part, which means that is the good thing, that if this part goes to this part, then this part is 1, 1, but then this part will be a bijection because it's a finite group. So this is bijective. Okay, probably this is a little bad, so I'll just put 12, but 2 is probably not fun to think about it. This will become a bijection just from the fact that it's an injection. And restricting an injection is still an injection, but an injection becomes a bijection because you're in a finite case. So different flavors bringing about these things. Easy, but nice. That means that all I'm trying to say is that this part, okay, yeah, so that's where I'm wrong. Yeah. So what I was trying to say is that this part should go to this part. Can you prove? This will just be about some set business. Yes, this must be on to. So I mean this must certainly be on to, right? Otherwise, who will go to 0, z, 0, n? These people should go, right? From 0, z only. Right, you agree? So this has to be on to. But then it means that this has to be a bijection because it's already injection, which means that which means that you are done, right? Which means that 0, z goes to 0, z and okay, I'm sorry. Why am I making these mistakes? 1 minute, okay? So this is shrink. Yeah, if you can first review a little bit of these things, then you try this if you want to, but let's see. So what we know is that this 0, z part, you understand loosely that it should go inside. So maybe if this is psi, right? Then what I'm trying to say, this should go inside 0 cross z. No, that is not correct. I'm saying, yeah, that's a problem. I have to now introduce some new symbols which might confuse. Psi inverse of this, right, should be contained in this. Yeah, or yeah, wait, this will confuse. Okay, let me see if I can find an easy way to explain. So see, yeah, I should say that first. The goal is to show that psi of 0 cross z is inside 0 cross z, correct? If you can show this, you are done, right? Then it will become like this, and then it will be done. If you agree to this, that this implies that it is of this form, right? The psi of 0 cross z, you should go to 0 cross z is what we are trying to show. Yeah, what is a good way? Okay, so if you just say that psi of 0 comma n goes to some a comma something, where this is some phi n, because this part will also be a group homomorphism. Yeah, then then also it can be, I agree, this part is slightly complicated, so you can, maybe I'll need some time to say this. Yeah, that kind of thing can always happen, right? Yes. Yeah, but then, so this cannot happen because you'd see, if this happens, then you have a map, basically. I do say this properly. It's, you have to project it onto the first coordinate. Okay. Maybe I will probably, are you guys following this? Is this okay, or it's a bit confusing? I don't know.
Confusing.
Right? Because it's, but this is the extra part. I mean, this is just the extra part we're exploring. But what I'm just saying is that you can take this, and if you look at the image of this, then that will also be a subgroup, and that subgroup, if it intersects with z cross z, then you project it onto the first coordinate, then you'll get a map from z to okay, that is not a problem. So I am slightly wrong in the explanation. Okay, anyways, I mean, we can think about it maybe later. Vaishnavi, please think about this question. Okay, we can discuss this. Okay, then let's meet on Thursday, and probably we'll start with some elementary problems, unlike last time. Maybe we went a little. Okay, right, so let's meet on Thursday. I'll do some analysis. I mean, I don't know if you're coming, that's optional. So Thursday 8:30 p.m. Okay, I stop for today. This part is all right. Okay, bye.